We are very honored here today to have Jacob Cohen. Jacob is the chief scientist of the NASA Ames Research Center and has in-depth experience in leading fundamental research and technology teams to directing multi-organizational efforts aimed at transferring research results to applications. He has a proven ability to develop new concepts and technology to communicate with interdisciplinary staff such as engineers, scientists, managers, and non-scientist personnel, which I can imagine is quite a difficult task to do, all to ensure that we deliver an end product. So without much avail, Jacob Cohen.
All right, thank you for the introduction. It's great an opportunity to be part of this, what do we call it, educational promotion of new generation, really up my alley in terms of trying to get people to see the world the way I see it, which is important. The second part, that introduction was a great introduction, and what it all means is what I do is I try to persuade my management to focus on areas that are of my interest. And at the end of the day, hopefully that links in with what is the interest of NASA and the rest of the world. So I want to talk today about NASA Ames Research Center and what we do at the center. And then I'll give you a little bit of my 2 cents. Hopefully I won't get in trouble. So NASA Ames Research Center is at one of the greatest places in the world to work at. There are really great historical places around the world, but NASA Ames is in the Silicon Valley of California. So what's great about there is it's a hub for high-tech, biotech, and of course it's where NASA Ames is. We are not the largest of the NASA centers, but I consider us to be a very influential center as a research and technology centers. NASA has 2 different main centers, research and technology and space flight centers, and we are research and technology, and as chief scientist, that means we push the envelope. The center has about 2,500 employees. Half of them are civil servant, that means government employees, and the others are contractors. But it's really what's important about our center is every summer, we have about 1,000 students that come in. So think about what we have coming into the center. What does that mean? That means we get new ideas flowing into our center, and we also motivate the next generation. We work, as I like to say, on things that change the way you see the world and interact with the world. And let me just go over a few of these. So first, if you're going to interact with the world, you have to have partners. And what we have is we have a research park right next to us. That research park has commercial and academic partners that are related to what we're interested in. And it contains a whole list of them. Some of them are really big companies, some of them are small companies, some of them are companies that spun off of the center itself. So if you have an idea and want to work next to Ames, well, you could work on the Research Park Center area. So yes, I wasn't at NASA Ames when it started, and I wasn't at Ames when, before it was a NASA center. But we've had over 75 years of innovation. If you plan on looking at any re-entry vehicle, you will notice that it is not in a sharp, pointy connection coming into the atmosphere, but a blunt re-entry, and that work was originally done at Ames. This just gives you an overview of the type of innovations that occurs at the center, whether it's aeronautics, which is the beginning of any of the space agencies that exist, all the way to now and looking at biology and how biology influences it, and looking at space on our Earth to understand what happens here. Sorry. So what are the current competencies? The center is divided into 8 competencies, but they all interact with each other. One, which is historical, is air traffic management. If you think about it, it is a critical part of the infrastructure for air traffic. We optimize the software and the programs that are needed for the management of both commercial airplanes and others. We also now work on unmanned vehicles and the traffic management of unmanned vehicles and what that means. I mentioned blunt body. We are also the center for materials for entry systems, specifically the shielding. So if you're interested in re-entering any atmosphere, we are one of the centers that does the re-entry material that will protect your vehicle. We wouldn't be at Silicon Valley without advanced computing. So you have basic advanced computing, like the supercomputers, and Ames has computer systems that are either top 15 fastest or top 10 fastest civil supercomputer, depending on when you want to look at it. For some, that is really important. Why is that important? Because we could look and do complicated analysis, whether it's analysis for how a vehicle lifts off, to water temperatures across the globe, to agriculture that you want to do. But where is the next part of computing? Some will say it's in quantum machines. So we at Ames have a quantum computer. Now, is it truly quantum? Well, it's research. So is it truly in the quantum sense? But that is not the question. The question is, you have a capability, how far could you stretch that capability? And what does that tell you about analysis? Intelligent and adaptive systems. One of the things that is really important is standardization and modularization. And if you look at adaptive systems, intelligent systems, you'll see that whether it's from the ground to the space, there are core interactions that vehicles have to do and analysis that they have to do about their environment. So understanding it and optimizing those questions is another area that Ames advances on. Low-cost space missions. Well, we're in Israel right now, and Israel is known for small payload missions, just because how they get their satellites up into orbit. But Ames is also an expert in low-cost space missions or small sats, and I'll give you some examples of that later. Aerosciences. If you want wind tunnels, we have the largest wind tunnel. What you didn't hear is that my background is in biology. So I'm a chief scientist of a NASA center, and I'm not a physicist, I'm not an astronomer, I'm a biologist. Ames is the center for fundamental space biology at the agency. We advance astrobiology, we look at life support, but more importantly, we're looking at application of biology for space exploration. Because I, like others, believe that the combination of biology and engineering is where we're going to go if we're going to do deep space exploration. And lastly, we need to make sure that we survive. And we do that by studying our own Earth. We go out there into space and space exploration in order to learn about ourselves. And we have a whole division that looks at Earth science, whether it's fires, whether it's looking at weather changes, or so on across the globe. So we'll break this up, and these are the core areas, and I'm going to try to leave time for questions and to also give you a little bit of my viewpoint of what we do next in space exploration. So I'll go through these next few slides pretty quickly. If you have questions, just ask me at the end. So science at Ames. Well, it's really an important area. Why? Well, we have the International Space Station for first. It is a station that is A, built on collaboration, but B, its main focus really is to test things, to learn about things. And we built hardware to do experiments on station, and we have researchers that do work there. We have lots of collaborations that advance different areas of science, including planetary sciences across there. So we touched a little bit about aeronautics, but let's touch a little bit more about what the future is. Recently, we had a conference at Ames looking at how to manage unmanned vehicles. Now, we're talking about things like, I want a delivery tomorrow. What's the fastest delivery? How do I get a system that delivers something without crashing into things? How do you interact between a manned vehicle and an unmanned vehicle? How is that controlled and managed? So exploration technologies. We talked about these different categories, but what we miss is the interaction between the human and the machine. If you're going at a certain gravitational field, like taking off on a flight, what is your visual senses? How are you going to press on those buttons? If you need a parachute to land, let's say, on Mars, how do you know your parachute will deploy correctly and work? How is the design going to be implemented? So here I will spend a little bit more time in small sats. Just like everything else, like our computers, like our phones, we're continuously improving and shrinking the size of the technology. We could do a lot with satellites now that are the size of a cube, or even smaller. That gives you a lot of advantage. It allows you to repeat things, which is, as a scientist, is a hallmark of making sure that you understand the system. So we have over a 60-year history of small spacecrafts, and here I'm just showing you recent experience with small vehicles. When you're at an agency like NASA, you're surrounded by engineers. Maybe most of you are engineers. So if I'm going to say something that offends you, please forgive me. But engineers are there to have fun. And so sometimes they don't want, well, let's put it this way. If they're given a project, they want to start anew. They want to make sure they started from ground zero in their design. That's good. That's a lot of fun. But it's costly and takes time. So the trick is, how do you reinvent? How do you adapt? Right? That is important. So the more you're able to do that, the quicker you could respond, the more science you could get out of it, and the more advancement you could do. So here are a few examples. For lunar missions, we had the secondary payload called ElCross. I'll go into each one of these in a little bit more details. We had landing, and then we have an upcoming mission. We had HIRIS, and we had tests coming up. But I'll start with Kepler. Kepler is an interesting satellite. The PI thought of the idea about 30 years ago. The technology didn't exist to do it. It's a very simple technology and concept. Basically says, if there's something rotating a sun or any light, you will dim the light when it goes in front of it. And by dimming the light, you could determine size, distance, the periodicity that the planet was around it, and if it's a planet. So when we started space exploration, that is when we were in the cave stage, we looked up and we thought we were the center of the universe. Well, what Kepler tells us is that there are planets everywhere. Everywhere you look out there, there's planets. That's interesting, because we always think of biology of Earth as very unique. So now we know, with this simple mission that's still ongoing, by the way, that there are planets everywhere. And not only that, there are planets that are potentially in the zone that is called habitable zone. Well, they are in the habitable zone, but they're potentially like us in terms of size and structure, which is important because it says something about the planet itself when it's that size. So we changed the books in terms of how you see the world around us. So let's get to ElCross. ElCross is interesting. It's a secondary payload. That means there was a primary satellite. It was done as the second payload on LRO mission. It uses the ESPA ring, which is a ring that's usually used to carry small CubeSat missions and deploy them across there. And we used it to make a satellite. And its main purpose was to say, is there water on the moon? And guess what? There is water on the moon. It was low cost, and water is important because water is important for space exploration. LADI started from an exercise of looking to how do you modularize satellites. If you have a modular system like Legos, you could take the satellite and make it into an orbiter, or you could make it into a lander. You could make it larger, you could make it smaller, and you could change it to the location that you want to go for. This was also a small satellite that was completely built at Ames. It went and looked at both the dust and the atmosphere of the moon. Yes, there is what's called an atmosphere of the moon. But even though those are called small sats, there's a range of satellites called Nano Sets. And we, as a center, pushed Nano Sets from being something that you use for education, something that you use to learn systems, to actual applications. So we had biological payloads that were flown on nanosats. First with GeneSat, and actually before GeneSat, there was something called GeneBox. And GeneBox wasn't a satellite, it was just a test of the system, and we flew it on the Bigelow vehicle. Some of these were flown on Falcon 1s, and I don't know if I was fortunate enough, because I was the program manager at headquarters that paid for it, but one of the vehicles was experimental, and our little satellites, which is pre-sat, as you could see it, is now in the ocean somewhere as part of it. But it's important for pushing the envelope. But we also, from this, also are developing other scenarios to utilize it, whether it's doing multiple CubeSats, or our current version, which you see, BioSentinel, flying CubeSats to way into space, to where the moon is, and so on, to do biological experiments. But besides NASA as a center, we also have these virtual institutes, because the world is virtual. We have 3 virtual institutes with global and national partners in those. We'll start with astrobiology. This is a key driver for why we explore space. We explore space to know whether we're unique. We explore space because that's an innate structure of what we need to do for survive. By going out there, we will know how far life exists. Aeronautics is another institute, and now is a very hot topic. You have lots of people flying unmanned vehicles, and we're continuing to develop and standardizing approaches for it. Solar system exploration is another one, and it covers most of everything else that you can think of in the solar system. And this is also an important area for us. So I have this up, and this is where I go off the topic of talking in Ames and giving you a little bit of my personal viewpoint of space exploration. That's a planet, and it's planet Mars, and this is where I want us to go. Personally, why? Well, first of all, because science fiction says so. See, it's not very scientific, right? Science fiction said we should go to Mars. Actually, when we first looked at Mars, we thought there were aliens on there with little canals at the time. Well, now actually we know those canals are probably flowing water, which is interesting. So science fiction drove it, and if you don't believe that science fiction drives reality, well, you could look at this in the cell phone. Star Trek and the cell phone and back and forth. It's an important component of space exploration, is our imagination. We imagine what the future will be, and then we actually discover that it is there. But there's another reason as a scientist. Mars is well explored. It's close by to us. There's an atmosphere there, similar to some of the early atmosphere here on Earth that could be used. We have water everywhere. Water is important for life. Water is important for most of the things that we invent. And the beauty of it, now it's also in the NASA strategic plan. It is part of the plan for us to go to Mars. It is part of the plan to do science there. It is also part of the plan to do collaborations to get there. So yes, all of you could be part of that future of going to Mars. And when you succeed, I succeed also, because that's where I think we should go. In between, we'll go to the moon, we'll go to other places, we'll spend other vehicles, but that will be the first step to do what Star Trek says, and that is go even further out. Here is what looks like, to me, like a funnel, like a technology development funnel, like an innovation funnel. This is the funnel that NASA is looking at all the investment that it does, and looking at international investments to get us to the Mars destination. So it uses the International Space Station for life support. It uses vehicles that will go around the moon to test, re-entry, human vehicles, and so on. Partnership is at the center of Ames. We do a lot of partnership. The reason why we do it is because that's how advancement occurs. This is just a minor, small example of the number of partners we do. And if you could see, it's not just one particular area. It's international, it's commercial, it's academia, it's other centers within the agency. It is important to do that, because if you isolate yourself, then you close yourself to new techniques, new technologies, and new approaches. So if you want to implement things, partner and collaborate. So why partner? Well, I started this talk by saying I want to convert you all to see things my way. Well, that's one of the reasons to partner. The other thing is to gain knowledge and information from others and also see the world the way they see it. So expanding to the next generation, because some of this vision is not going to be implemented just during my time frame. So that is also a reason to collaborate. So focusing, short-term, long-term, looking at financial ability to do the work. There's lots of private entities that have made lots of money in the commercial entities and now are looking to space to do advancements. So collaboration there is important. But we are, at the end, just one planet. And so we need to join forces and collaborate in order to push forward with our vision for space exploration. So if you want to work with Ames, there are lots of ways to do it. Some of them require you to be a little bit more patient because it is a government entity, and some of them are faster. But if you're interested in collaborating, there is a method, there is an approach, and we're more than glad to work with you on figuring out that way. Whether it's just traditional grants that you apply for, to more substantial nation-to-nation agreements that occur. So one day, hopefully we'll go there. But really what I want to point out is something that I always do in every time I give a talk. And that is the key to long-term success in life is to have imagination, Mars and beyond, persistence. If you're going to do collaboration, you have to be persistent and build a friendship that helps you develop that collaboration. If you want to go into an area, a field that doesn't even exist in your country or your university, persistence is important. And lastly, compassion, because if we all think about each other, then we'll be able to move forward. So with that, I'll say thank you, and then we'll take some questions.
Are these mics working? Perfect. So before I hand the question and answer session to the audience, I have a couple questions of my own. So Jacob, you talked about the necessity of partnership with international partners, with different commercial entities, industry, academia, as well as within NASA centers. What is your definition of a successful partnership?
That's a little, I guess this is working. So it's an interesting scenario. It depends what your goal is. I think at first, if you have friendship development that occurs there, that's the initial steps of a collaboration. So I could tell you that I've worked on many scenarios to collaborate, and some of them have failed in terms of the ultimate goal of, let's say, a project, a specific project. But it's a successful collaboration because then both of us, rather than giving up, come up with the next concept that comes in. On the individual collaboration is when both sides win. And both sides win in different components. If it's scientific, a good publication is a win. If it's technology, a good mission. If it's politics, it's changing the way we see the world. So all of those are ways to collaborate across there. So you can't just limit it to one just area. And as scientists, you want to push the envelope.
Fantastic answer. You talk about the need for changing the world and changing how we interact with the world with science and technology and policy. Is there one mission or one discovery that you've seen in your career that you think has made the biggest difference with how we've interacted with the world?
So I think it's a little bit more complex than that. I could tell you what first jumped into my mind when you asked that question. And it wasn't during my lifetime. It was before, but not a lot before I was born, which was, of course, the landing on the moon, which really changed the way we look at the world. But I could tell you something that I used even in this trip. You know, I wanted to go from here to Tel Aviv, and I pulled out the phone and used a GPS system to get there. It interacts with us every day in that scenario, whether it's the communication of the phone, whether it's the transportation. So that is the importance of going to space. So that's the daily effect that I see.
Good. I think everybody appreciates Google Maps. I'd like to throw some questions to the audience. Do we have a roaming mic? Thank you.
Hi, my name is Daniel. I'm going to go a bit more sciencey. I'm an aerospace engineer. I deal with formation flying. And my question is, do you see a small sat, nano sat, CubeSat formation flying mission going further than LEO in the near future? Or if you have any examples, I would love to hear them.
Yes, I do, as a quick answer. There has been a few proposals already set in to NASA, and I'm sure to other agencies, about sending CubeSats. Some of them are not in pure formation. I mean, formation flying has different forms to it. But, you know, if you think about it, you could carry on multiple CubeSats on a primary satellite to a destination, release it, and be able to do multiple observations of the planet. And so that has been, I'm sure that there are multiple proposals. I know that because I was in one of those proposals that put in those. So I do see one of those occurring. There is a transformation of how people are looking at doing missions in space. There is the concept of Nobel Prize winning, large, multi-billion-dollar missions, international, truck-sized satellites that could find things. And then there's the balance that says, well, if I fly many of these, small, they're low cost, and they slowly chip away on the science that is being done. And people are gaining the grounds. The technology is getting better, the data is getting better, and we'll see more of those.
Well, thanks for the great talk. I'm from JAXA. My name is Jun, and I have just a quick question. How far do you believe the manned Mars exploration in 2030s?
So that's policy, and I went into science. I actually think that going to Mars, while there's true complexities in going to Mars in terms of human safety and all of those areas that we want to be concerned with. But I spent some time at NASA headquarters. So I started at Ames, then I went to headquarters, and I came back to Ames. And when I was at headquarters, I realized that, when we were landing on the moon, Von Braun actually pitched to the president a method to get to Mars, very similar to what currently is going on, and we still didn't implement it. Now, when we went to the moon, at some points, there were some storms that could have affected our astronauts. But we didn't know much about that at the time, and we took those risks that go there. So it really depends on two things: the motivation of society as a whole to go to Mars, and the second, which I learned from the engineers or the orbital mechanics folks, is when the best time to fly and get there. Now, I even have a more radical viewpoint of trying to get there, and I think that there are multiple approaches. There's the standard approach. But I think if you start sending things out there to develop a mission to go there, you will improve it and you'll get there. So I didn't answer your question of 2030 because it's really up to everybody else. But if we wanted to make it, we could make it.
Hi, my name is Hein from Rutgers University, and I was wondering, as a biologist, would you agree with the statement that the quickest way to get people to Mars successfully would be first to send people to the moon and figure out all the issues?
So I apologize again. Trying to get over a cold, which shows that small organisms could affect large organisms. I think there are different debates about whether Moon is the best place to do as a stopover to go to Mars. You could go to Mars without going to the Moon, and you may see some groups to try to do that. And you could go also to Moon and do risk reduction. It's the question of when are you going to be satisfied to go over there, right? Every time you're going to do a space exploration mission, there are going to be some risks associated with it. So, at one point NASA said, first we're going to go to the Moon, then we're going to go to Mars. And then there were people that said, let's go to Mars together. For me, it actually makes no difference. I think there are some risk mitigations you could do at the Moon. There's some risk mitigations you could do on the ISS. But it's not necessarily that you have to do that in order to get there. It's not a requirement.
I'm Heinz Stöber from Germany. I'm afraid I have another policy question for lots of reasons. You collaborate with some of the NASA centers, but you also compete with them in certain ways. In planetary science with JPL, in Earth science with JPL and Goddard, and in Mars with a number of the centers around. How to decide who does what and in which form do you collaborate, in which form do you compete?
So I'll give a little bit of policy inputs. As in management, I get to see some of the stuff that NASA is doing, I hope. So NASA is actually looking at levels of duplications across centers. What do we need to have duplications and what we don't need to have duplications. So let's say, I know this is a sensitive issue between different centers, but right now Ames is the single ArcJet center for the agency. There were 2 centers that did ArcJets, and now there's a single center that does it that has all the capability for the agency. But to give another example, if a wind tunnel experiment needs to be done and there's only one wind tunnel and it breaks down, if you don't have a backup, then you delay all those experiments. So those are things that are being weighed because budgets are limited on what we do and what we don't do within those areas. But in terms of competition, well, there's competition also within the center. A good, healthy department will have colleagues that are also competing for same funding. And so I think it's useful to have the competition across there, because if we don't have competitions, we don't have different ideas to select for. And so it depends on the level of area that you're looking at. If you're looking at research, you should have competition across there. If you're looking at technology and infrastructure, you have to see what is the risks that you're willing to take if you only have a 1-point failure in your organization. And so that's the policy, and some of it is being analyzed right now. There's a process that's going on in the agency looking at that across the agency itself, as I'm sure other organizations like ESA are doing also when they're looking at whether one country has the capability to do launch vehicles or another and so on within those areas.
I think there's a question at the back.
Sure.
Yeah. Henning Rodell, and I have a question about partnerships and commercial companies, and a lot of that comes through the space portal. And the question is, I mean, getting an SAA is very important for a lot of these companies starting, and that may or may not continue for policy reasons. What needs to happen in order to get beyond that, in order to kind of start without the need for an SAA?
So there's a couple of different areas that you could work without SAAs. SAAs come into, maybe let me see if I can move this backwards. So here, so if you look at the Space Act agreements, it actually, Space Act agreement, all it means is that NASA has really some authority to do interactions with commercial and other entities when it was developed, because it was developed in part, and what people forget is not just to do space exploration, but do collaborations and education across there. And so you have those types of collaborations that come in, but sometimes you have collaborations that occur through a normal grant that is applied first to before a Space Act. So a company could partner with a PI at Ames or in other centers or anywhere else within the government agency and apply for a grant, and then you do the paperwork that's associated with it. But you could also do these small business and innovations and so on. So it really depends on what type of collaboration you're doing. If you're doing a non-reimbursable type of scenario, then you will be sort of stuck with the Space Act agreement pathway. But NASA has been really good at trying to optimize and make that more efficient. It's not perfect yet, but they're improving it. You know, that's the main area, but if you're looking to, on a particular area, are interested to collaborate, where you're not interested in doing some of those Space Act agreement levels, then you could even contact me and I could get you in touch with how to process that.
There's a question in the front.
My name is Pirawan. I'm from NASA Langley. I have a question regarding to the fluctuation of funding from NASA. So how does that affect to the you know, the collaboration with the partners, and how do you maintain the direction of the research at Ames and also the, you know, the relationship with the partners?
So there's 2 parts to it. Fluctuation does occur in budgets because NASA, and in particular centers, don't create their own budget. It's congressional within our government, the system that we have it. I think that we've been lucky, though, at the agency that we've had pretty much a level budget that comes in. We have more things that we want to explore than we can, and that's why collaborations come in. There are different components of maintaining fluctuations. There is keeping the experts that you need to gain budgets to those areas. Within partners, communication is really important. We pick things that are, so I will say there's an advantage to having an international or a national partner in a topical area that you pick. Let's say you wanted to do work on International Space Station, on, I don't know, movement of molecules or colloids or any of those type of areas. If you're just you yourself as a national person in the government, you'll get a budget resource. If there's an international component, the other government is also funding it, so it's a lot harder to move that. That actually creates more stability to the project itself along it. But I think overall, if you look at it, we've been relatively stable. There are things that you tune out in terms of what's important and things that you put more emphasis on because you are an evolving exploration scenario. So it's not like necessarily just pure academia where you'll always have a topical area in one area. Some areas become less significant and important for the agency. So, you know, overall budget, not up to us. Internal to us, absolutely great scientists, great engineers, and you'll have a stable budget.
Jacob, so this panel is actually, or this Q&A is part of the YP program of the IAC, and I see quite a number of young professionals and students in the audience that are IAC delegates. And given your diverse career within the space sector, I was just wondering if you could give us a few words of inspiration to the next generation.
So first of all, never give up. That's the first thing. No, I think, you know, it's really interesting. I mean, when people start in the industry, they sometimes don't know where they want to go, what they want to do, or sometimes they do and they can't find the right niche to work at it. You know, when I came to Ames, I started as a researcher. I came not really knowing what space biology is about, actually. Because when I started, I was doing evolutionary biology on viruses and others. But I do remember skipping school to watch the shuttle launch, right? And so I came in and said, wait a minute, space is a great punctuated event. It's an event that creates speciation and will be a great opportunity to study. During that time, I moved also into management at certain points. So if you're looking to contribute to this area, realize two things. This is the future. So if you were, I think there was a movie before my time called The Graduate. And in that movie, I think the husband of the wife, Robinson or something, said to the, I don't know the name of the actor, said, the future is plastics. And actually it is. Most of us have plastics around here. And just to point out, plastic is biologically derived. I'm not biased in any which way. But space is the future, and that means there's opportunities. And the opportunities are for you to contribute as part of a team, if you want to do that, or for you to contribute in pushing the envelope to something new. Both of those areas are available, and they're available everywhere around the globe. That's because space is no longer just limited to one or two nations. So there are lots of ways to push it. And the benefit of it is that you're changing the way people live and see the world every day, here, now. So keep on moving to that area. And if you don't want to see Mars, you want to see, we had a question about Moon, that's also fine.
Very good. There's a few more questions. There's one just right in the front here.
Hello, Jean-Dominique from Airbus Defence and Space. You mentioned about the impact of the science fiction and entertainment industry on, you know, scientists and researchers. So I think it definitely motivates all of us to go to work in the morning. But when talking about actual program approval and implementation, I have a strong feeling that it's the other way around. That there's some office at NASA that actually tells Hollywood to, hey, let's make a movie about Mars, so then we can get money, you know, to get public approval, etc. So do you have something to argue about that?
So the question is, do we help push science fiction?
Yeah.
Well, we do also, and that's because we inspire the science fiction writers. So I'll give you an example. We have a summer series at Ames that we put on, and we invite various speakers. This summer, we invited Andy Weir, the Martian, to Ames. And he talked about the making of The Martian and how science helped him and inspired him in writing the book. At the same time, when he's there, we're talking to him about technologies that we think are in the future, right? So guess what's going to happen? Somewhere along the line, that or other people's technology and discussions flow into what comes in. So a good science fiction book, as I say, it starts with reality and then merges you into the world that is science fiction. And you sort of almost don't notice it as you go through reading it. So you have to start with what reality is. Then that science fiction needs to be semi-possible. And guess what? We have organizations like NASA in the US and DARPA that take challenges that say the semi-possible, let's see if we can make it a reality. So that's that flow, the circle that comes in through there. We do have a great PAO organization at the agency and at the center. Continuously improves more. They help us interact with the world outside because, sometimes geeks and scientists don't do such great interaction. And so we do have some help within that area.
Thank you.
Is another question on the left? Oh, there. Oh, on the left?
Our left.
I couldn't help but add on to your comment about the boundary between science fiction and science reality. My name is Larry Young, a professor at MIT. I'm also chairman of the advisory board of the NASA Innovation of Advanced Concepts. And this is an opportunity that you should look into when you have a really revolutionary idea just a little bit beyond the current development phase. And they do fund small revolutionary notions for 1 year for $100,000. I must say it's limited to work that is done in the United States, not necessarily by US citizens. But if you'd like to look into it, there's an annual call for proposals. The website is nasa.gov/NIAC, and I recommend it. I think this group is well matched to it.
Thank you very much.
And let me add a little bit to that. If you have crazy ideas and want to try to figure out ways, not that I am a funding organization, I'm more than willing to help. You could look me online, send an email, and we could discuss it. It means you have to do work. It's not that I do the work, but I'll help guide you to do that. There are always ways to try to innovate, and that is really important.
I think you might get a few emails after this. So Jacob, when we first met, you described yourself in high school as a geek who wasn't very good at maths, but tinkered with rockets. If you had to give yourself some advice in high school, in hindsight, what would you say to yourself? Putting you on the spot a little bit.
Wow. Well, I still didn't improve my social interactions as well as I were in high school. Actually, in high school, I was, one of the things that I did is I pushed a lot forward on areas that I was really interested in. And I only broadened those after grad school, in reality. I was so focused, did rockets and stuff like that in 5th grade, but somewhere in 6th and 7th grade, I got into biology and evolution and continued through that. I did fruit flies in my house. My parents' home had a fire or so at one point. Anyway, it's a big story. But the reality of it, I went through and did a PhD on fruit flies also. Right? I continued with that focus. When I went to advisors and they said to me, Jacob, you should think of this, you should think of that, I said, I know what I'm doing, I'm just moving forward with it. And then I realized as an evolutionary biologist, it's good to have a broad sense of things. So I would actually broaden the aspects. So if I was back in high school, I would broaden the research categories I would look at, but I would still be a scientist.
Jacob, thank you so much for your time today, not just for presenting about NASA Ames and reminding us about the back and forth between science fiction and reality, but inspiring myself and so many of the young professionals here. So thank you again for joining us.
Thank you. Thanks.